So mechanical energy. It's a combination of kinetic and potential energy. So you have kinetic plus potential. This is known as mechanical energy. All right, so that's known as mechanical energy. All right, so E is our mechanical energy. Conservation of mechanical energy means E is constant. So the constancy of mechanical energy is known as the conservation. When somebody says energy is conserved, which means that the energy remains constant. Okay, so if the mechanical energy is constant, look what happens. If the mechanical energy is constant, look, when you drop a ball, what happens to this potential energy? It goes down, right? What happens to this kinetic energy? It goes up. So the potential energy goes down, the kinetic energy is going to go up. So when the so what happens to the mechanical energy? It remains constant. If the mechanical energy is constant, potential energy turns into kinetic energy. Potential energy turns into kinetic energy. Potential energy turns into kinetic energy. When I throw the ball in the upward direction, what happens is kinetic energy turns into potential energy. So the motion gets converted into height. So when I drop the ball, potential energy gets converted into kinetic energy. All right, so when mechanical energy is constant, kinetic energy turns into potential energy, and potential energy turns into kinetic energy. So the question is, what conserves mechanical energy? So if mechanical energy is constant, and that's a big if. So what happens is when the object is falling, the potential energy is going to go down. It's going to turn into kinetic energy. When you throw the ball in the upward direction, what happens? Its kinetic energy is going to go down as its potential energy is going up. So which means that its energy, kinetic energy turns into height. It turns into potential energy by the same amount. So when the mechanical energy is constant, or conserved, what happens is kinetic energy turns to potential energy gets converted into kinetic energy. All right, so kinetic energy gets converted into potential energy, or potential energy gets converted into kinetic energy. So the next question is, what conserves mechanical energy? What conserves mechanical energy is a conservative force. All right, so any force that conserves mechanical energy, any force that conserves E is known as a conservative force. And obviously, the prime example that we're studying so far is gravity, guys. Under the influence of gravity, by doing work against gravity, you lift something up by doing work against gravity. All right, you literally have to do work against gravity because gravity is applying a force on this one. All right, so you lift something up by doing work against gravity. You're lifting this up against gravity. It's got weight, right? So the amount of work that you do is going to go into the potential energy of this. When you let it go, what happens? The gravity is going to take over. Gravity is a conservative force. So as soon as gravity takes over, what happens? It turns potential energy into kinetic energy. It turns potential energy into kinetic energy. Potential energy, the amount of energy that can potentially turn into kinetic energy. That's what it means. Okay, so you store energy in an object. When a conservative force takes over, it takes that energy and turns into kinetic energy. It's a very powerful concept. All right, so it's a powerful, powerful concept. So any force that conserves E, mechanical energy, is known as a conservative force. Example, gravity. Gravity is not the only force, but that's the only one we've seen so far. So gravity is a conservative force. The other one is a restoring force, like a spring force. Okay, we haven't really dealt with restoring forces yet, but we will. All right, 8:34. All right, let's just take a break for 10. Okay, so when gravity is the only force acting, what happens? The mechanical energy is conserved because gravity is a conservative force. Okay, notice that the op potential at this point, when you drop a stone, and then potential energy gets converted into kinetic energy. So on impact, it's going to be all kinetic. Mechanical energy is constant, so when the object is dropped, potential energy goes down, the kinetic energy goes up. All right, so pick out the best answer and put in the chat. Okay, very good. So kinetic energy, if the kinetic energy decreases, potential energy is going to go up. Is the best answer. All right, so give yourselves 5 points for that one.
The four-man bobsled, one of the world's most dangerous sports.
It's a 1,400-pound bullet going down, and you have to go down and thread the needle. You have to thread it right.
No seatbelts, no airbags, no brakes.
There's very, very little room for error.
Each time these racers take the track, they risk major injury, paralysis, even death. Big class in New York. The U.S. bobsled team digs in at the starting gate. This notorious stretch of ice has taken its toll on many racers. But Chris Coleman and his teammates are determined to make their mark.
In our practices, we're doing extremely well. We're having the fastest times down the hill. The ice was very, very smooth, very glassy. The team's extremely excited.
The team stands at the ready as their pilot launches the fiberglass hull downhill. The sled quickly sets a record-breaking pace, rocketing through hairpin turns at lightning speeds and soaring down straightaways at 90 miles an hour. Entering turn number 12, the team is on course for a new track record when disaster strikes.
All of a sudden, there's a silence.
The sled hits the turn too fast and too high.
And before I knew it, I was on the side. And then I said to myself, oh my God, I'm in a crash.
The bobsled spirals upside down, hitting the racers next to the ice as they hurtle down the track, slamming into turns with crushing force. Finally, the sled reaches the end of the line and limps to a stop. Crew members scramble to free the battered team from the wreckage. But only 3 of the bobsledders are able to stagger to their feet.
I remember the other guys getting out, but I remember I just couldn't move and somebody pulled me out.
Chris lies motionless as paramedics check for spinal injuries.
No.
To the relief of teammates and crew members, Chris can move his arms and legs. Incredibly, he suffers only minor injuries and is able to race again just a week later. This time, capturing the silver medal.
How did they know that they were going at 90 miles per hour? Okay, so they don't have any rolling tires, so they don't have a speedometer. And the only way they could have known that stuff is if they were using a radar gun, right? Is there any way you could actually estimate something like that if you didn't have a radar gun? Okay, guys, yes, absolutely. You can get a really good estimate. Number one, they're sliding on ice. You can ignore friction. Ignoring friction, what's the only force acting? It's gravity. Mechanical energy is not going to change, so it's going to remain constant. Potential energy depends on the initial height with respect to the final height. So what happens is potential energy goes down, the kinetic energy is going to go up by the same amount. Okay, so that's the way to do that.
And nothing pushes the G.
Case in point. So this is going to be problem number 6 from the handout.
Forces like starting high and dropping fast. Japan's Fujiyama is the tallest, fastest, and most expensive roller coaster in the world. The first hill is 259 feet high. Top speed, 81 miles per hour. It's like falling out of a 12-story building, only faster.
Okay, so what
And
we know.
nothing. Top 259
Okay, so the highest drop is
feet high.
going to be 259 feet high.
Top speed,
And at the bottom,
81 miles per hour.
it's going to be 81 miles per hour. Okay, let's check to see if the numbers check out. Okay, so what do we know? The tallest hill is going to be 259 feet, and the high speed is going to be 81 miles per hour. Okay, so let's just set this up. This is the only example that we will do today. Just want to have one single example. All right, so it's the first hill, and then I'm going to measure the speed at the bottom. In terms of meters per second and miles per hour. I'll take the final height to be 0. All right, so we will measure that with respect to the lowest point in motion. And this is initial height is going to be 259 feet. Okay. Initial speed is going to be here, so this is going to be 0. This is going to be our initial height. Okay, we will ignore surface friction because I'm looking for an estimate. We will assume that the only force acting is gravity. Okay, so with that assumption in mind, initial and the final mechanical energies will be the same. All right, so if you make the assumption that gravity is no force acting, initial and the final mechanical energies will be the same.
You put question mark for V initial.
Okay, very good. That's a mistake. All right, give yourself 5 points for that one. This is the final speed, right? Oh, the initial speed is going to be 0. Okay, so the conservation of mechanical energy means the initial and the final mechanical energies will be the same. Combination of initial kinetic and potential energies will be the same as combination of final. All right, so combination of initial kinetic and potential energies is the same as the combination of kinetic and potential energies of the final case. Kinetic energy is here, potential energy is there. Okay, it kind of looks nasty, but it's not. Okay, so the initial speed is going to be 0, so this term drops out. The final height is going to be 0, so that term drops out. This one is 0, this one is 0. All right, so this is going to be 1/2. All right, so the final kinetic energy depends on the initial potential energy. Get rid of m, so the mass doesn't matter. And get rid of 2. Okay, so here's the square of the final speed. All right, square and square root will cancel. All right, so here's the final answer. Okay, so you plug the numbers in. Okay, so when you plug the numbers in, I got 85.53 meters per second. Converted to miles per hour, this is, no, I got the numbers wrong. This is 39.74. 39.74. It's the same as about 89 miles per hour. Okay, they got 81, we end up getting 89. Why? All right, so our calculated number is 89. So that's in theory. Real number is real number is 89. This is the measure value. All right, so why is it that we end up getting 89? The real number is 81. Okay, so the real number is 81. We end up getting 89 miles per hour. Okay, the reason is because we end up ignoring friction, guys. Okay, so these kind of calculations are used for estimate purposes. This gives you a really good estimate. All right, so without the air friction, without the surface friction, it's going to be 89 miles per hour. And then you can deduct like 5 to 10 miles per hour from it. And it gets you very close to the real number. Okay, guys, for the next half hour, you guys